Before collision, we know the magnitude of the velocity of the moving body A. We know that angle, alpha, it makes with the x-axis, is null. We also know that body B has zero velocity. We need to find the magnitude of the final velocities of both bodies, via F and VBF, and the value of angle alpha. Angle beta is given by the position of the balls when they collide. Our method, as always, is to resort to the conservation of momentum, and of kinetic energy. Since momentum is a vector, momentum will be conserved along the two axes, x and y. So, we must consider the components of the velocities along these axes. Please, check the equations for the conservation of momentum, along the two axes. Since the collision is perfectly elastic, we will use the equation for the conservation of kinetic energy. Remember that the body B is not moving before the collision. We have two equations for the conservation of momentum, one for each axis. Since the masses of the bodies are equal, divide all equations by m. Divide the third equation by 1/2. Square the two first equations. Add the squared equations. Reorder the terms of the long equation. Remember trigonometric identities. An intricate equation reveals its inner simplicity. Recall the equation for the kinetic energy conservation and equate both second members of the equations. Cancel common terms. Since the velocity of any of the two bodies is not null, after collision, cosine of angle beta minus alpha must be 0. So, beta minus alpha is equal to 90 degrees or equal to minus 90 degrees. We conclude that the two final velocities have perpendicular directions. As beta is given as initial condition, we should write alpha equal to beta plus 90 degrees or alpha equal to beta minus 90 degrees. Direct the x-axis according to the direction of the velocity of body A, the incoming blue ball. The incoming ball can hit the standing ball on the top half or on the bottom half. Accordingly, apply one of the formulas. If the x-axis is opposite to the direction of the velocity of the incoming body, we have the same two situations. Each one, call for one of the formulas. Check the four possible situations which can occur. Notice that the incoming ball arrives over the standing ball, with positive velocity. No matter the value of beta, angle of attack, alpha is, always, equal to beta plus 90 degrees. Now, the incoming ball arrives under the standing ball, with negative velocity. No matter the value of beta, alpha equals beta plus 90 degrees. Now, the incoming ball arrives under the standing ball but with positive velocity. Alpha is, now, equal to beta minus 90 degrees. At last, consider the situation where the incoming blue ball arrives over the standing red ball, with negative velocity. Confirm that alpha, always, equals beta minus 90 degrees.
Remember that these equations work as the masses of the two bodies have the same value. We are going to solve the system of these two equations, in order to find the magnitude of the final velocities of the two bodies. But, first of all, we will make the angle alpha to vanish. We will keep beta, as it is one of the initial conditions. Since between angles beta and alpha there is a difference of 90 degrees, we have the well-known identities. Now, we only have the magnitudes of the final velocities as unknown values. Organize equations in order to solve the system. You can follow the known algorithm. Note that beta is negative, so it is sine of beta. Then V, A, F, gives a positive value, as it should be for the magnitude of any vector. We want that our equations give a positive value under every situation. So, we write them as, V, A, F, final velocity of the moving body before collision, is equal to V, A, multiplied by the absolute value of sine of beta. V, B, F, final velocity of the standing body before collision, is equal to V, A, multiplied by the absolute value of cosine of beta. Compare the two situations. If ball A collides, almost head-on, with ball B, it will transfer much of its velocity to the ball B, and its direction changes a lot. In the opposite situation, ball A keeps most of its speed and deviate much less. When the incoming blue ball collides, nearly head-on, it transfers almost all its momentum to the red standing ball. It's the situation we dealt in a previous video. When the velocity of the incoming ball has a diminutive projection over the line of action, we can predict that it will keep most of its momentum. See you in the next video.